The moon town in 2040 is developing quickly, and the residents need a safe and steady environment to live in considering the extreme temperatures of the moon. Selher is building a construction system to accommodate the residents. The system must be sustainable and to reduce wastage must be constructed from scrap. The system must be able to disassemble and assemble and should be able to convert into different shapes.
Normal day of residents. At 7 a.m. they wakes up and gets ready. 8 a.m. eats breakfast at social areas dining hall. At 9 a.m. goes for work minus workers and researchers. 5 p.m. goes to entertainment zone to spend some quality time, game zone, television, etc. At 7 p.m. they have dinner and at 10 p.m. they goes to sleep.
The key design drivers that we took into consideration were easy to assemble different units, easy to manufacture, modular, durable with respect to moon constraints, safety, and not extremely manual. After listing down our key design drivers, we moved on to affinity clusters. We categorized our affinity clusters into structure, material requirements, making, and construction constraints. The how might we questions helped us figure out and ideate our prototypes. We then moved on to benchmarking. Project Olympus is a space-based construction system that could support future exploration of the moon. Working with NASA's Marshall Space Flight Center in Huntsville, Alabama, the team will use a simulant of moon soil to investigate a 3D printable construction. A sustainable lunar habitat that will be the first human foray into extraterrestrial construction with robust structures that provide better thermal, radiation, and micrometeoroid protection than metal or inflatable habitats can offer. Another example that we came across for benchmarking was Buckminster Fuller's 100-meter hexagonal house, which was an earthquake and storm-resistant structure supported by a central pole from which cables would be suspended, allowing the outer walls to be non-bearing. By grouping all permanent utilities in the central pole and letting the rest of the interior space remain modular, Fuller created a flexible plan that would allow tenants to transform the space according to their needs. Not only would the house have been exemplary in its self-sufficiency, but it also could have been mass-produced, flat-packaged, and shipped throughout the world. The design displayed forward-thinking and influential innovations in prefabrication and sustainability. We then came across origami buildings. Origami buildings and structures have proved to be beneficial in space engineering. Origami is applied as a method of organizing luggage for space travel, increasing flexibility of spatial structures, and improving the accuracy of robotic motion.
Prototype 2. This idea is inspired by the Japanese art of origami. It is in the shape of a trapezium, fast construction origami pattern, easily transportable by disassembling the parts. The pole at the center gives balance to the structure and can be used as stairs. There are 2 floors in each unit. Each unit is 20 feet in height and 10 feet in width. These units can be folded and transported from one place to another. There are support stands on the exterior of the building to prevent it from folding down.
We then came across some locking methods which would be useful for our construction system, like slitting, lock and key, layering, and interlocking. We also came across inflatable bags. The bags were inflated in a matter of seconds using gas generators powered by solid rocket motors.
The first prototype is all about inflatable construction. The simple mechanism of using interlocking forms the skeleton, between which inflatable airbags filled with helium-3 are placed. Environment inside the structure. The skeleton is made up of simple joints. Depending upon the shape, the joint is made along with a rod, which would be then fixed into the joints to create the shape. The joints and rods would be made up of titanium. Moving on to the 3 ideations, the hexagonal structure is an ideation for housing, whereas the dome is for a hospital facility, and finally, the diamond structure is for a research facility. The main purpose of this prototype was to create an easy to manufacture and transport, multi-purpose, mobile construction and take advantage of the existing materials on the moon.
We evaluated our prototypes with the help of a matrix evaluation table, which helped us go forward with prototype 2 as it fulfills most of the requirements.
The actual size of the unit will be 1.5 feet times 1.5 feet times 10 feet, wherein the height and width will be 1.5 feet and the length would be 10 feet. This is how the structure will actually look on the moon in context to the astronaut.
The journey map includes the material is first mined from the mining site, then it is delivered through the rover Design and Challenge 2. The material is then delivered on the site of construction. After that, the individual block is made, and finally, the resident building is being constructed.
A recent ESA research showed that urea, the main organic compound found in our urine, would make the mixture for lunar concrete more malleable before hardening into a final, sturdy shape for future lunar habitats. Researchers found that adding urea to the lunar geopolymer mixture, a construction material similar to concrete, worked better than. Lunar regolith has many useful properties for construction on the moon. To complement lunar concrete, basic building structures may be formed from cast regolith. Cast regolith would be very similar to terrestrial cast basalt. Created by melting regolith in a mold and allowing it to cool slowly would allow a crystalline structure to form, resulting in highly compressive and moderatively tensile building. Based on findings of moonquake science and lunar regolith study in the past few decades, it is now feasible to develop technology of moonquake-proof structures using raw lunar soils. The developed lunar soil-based materials and structures should be strong, water-free, thermally non-conductive, durable, radiation-proof and low cycle fatigue resistant, energy efficient and air-proof.